Dr. Hartman, can you hear me? Because I don't think anybody can hear.
What about now?
You got it.
Dang it. Okay, thank you. Sorry about that. We're talking about instantaneous and average power, and we're going to be looking at a generic linear black box network first. Okay, so I just have a black box that contains some combination of resistances, capacitances, and inductances, and I am sinusoidally exciting that network. And what I'm doing is I'm going to effectively take the voltage drop across the network and the current flowing into the network like so. And we are going to make an assumption. It's not really an assumption here because I've explicitly stated that our network is sinusoidally excited. So my voltage waveform should be of the form Vm cosine omega t plus some phase angle theta v. And my current should be of the form Im cosine omega t plus theta I. And our instantaneous power, that is our power as a function of time, is simply going to be the product of that voltage waveform V of t and that current waveform I of t. So what I've done is I have introduced a couple of signals on Desmos. So hopefully you guys can all see the Desmos thing that I've pulled over. Somebody give me a phase angle between 0 and 90 degrees, please.
30.
30. All right. So I'm going to put 30 there. And I'm just going to choose for right now that my current is going to lag my voltage. So I just need it to be a number less than 30. 0 satisfies that. So let's look at things real quick, right? So here's my voltage waveform, sinusoidally oscillating from positive 5 volts to negative 5 volts. And we can see that it does indeed have a positive 30-degree phase shift because our signal hits its peak value slightly before t is equal to 0. When I turn on my current, we can see that our current is slightly lagging our voltage waveform. And when I turn on my power, we get this signal right here. So what I'm going to do is I'm going to turn off the current really quickly because I want us to make a couple of observations about what's going on. Okay. And this is just too busy with everything going on. So if we look at our power waveform, which is in green, we can see a couple of different things. Okay. So actually, let me turn that power off really quickly. So our voltage waveform is a simple sinusoid, meaning exactly half of the time it's above the horizontal axis and exactly half of the time it is below the horizontal axis, right? Same thing for our current. But when we look at just the power by itself, the signal is no longer exactly half above the horizontal axis and exactly half below. Instead, it has been shifted up by some amount. So our power waveform as a function of time includes some DC offset, okay? So that is a pretty interesting observation because if we look at our voltage waveform again really quickly, what is the average value of the voltage waveform?
0 volts,
0 volts. What is the average value of the current waveform?
0 amps.
0 amps. When we multiply those two together, we would expect, just based on intuition, that the average value of the power should probably be 0, but that's not the case here, right? So the average value would represent this point somewhere along this line where you can see my mouse, where half of the time it's above that line and half of the time it's below. So based on these numbers here, somewhere between 4 and 5 watts is what our average power should be. Okay, so that is an interesting result because it doesn't work the way that intuition tells us it might. Another thing, and this is going to require me to turn on one of the other signals. So let's just do the voltage signal for what it's worth. So notice that for every time my voltage signal repeats itself once, my power signal repeats itself twice, right? So in between the space of this positive peak on the voltage signal and this positive peak of the voltage signal, my power hits 2 peaks and then repeats. So it seems like our power waveform is oscillating at twice the frequency of our voltage waveform or our current waveform. So we've got some interesting stuff going on here. So let's throw this and see what shakes out. Okay. So I'm going to be using a trig identity. I do not expect you guys to know this, or nor do I expect you guys to remember this for the exam or anything like that. But I'm using the trig identity that cosine of some angle, let's just call it phi1, times cosine of some angle, let's just call it phi2, is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2, where angle 1 is the total angle omega t plus theta v, and angle 2 is omega t plus theta I. So if we apply that trig identity, we're going to have P of t is equal to, so let's start by just substituting things in here really quickly, Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. My Vm and Im can get pulled out, so then I'm just multiplying cosine angle 1 times cosine angle 2. So that's going to give me 1/2 Vm times Im, and then I'm going to have the cosine of angle 1 minus angle 2. So omega t plus theta v minus omega t minus theta I. The omega t's cancel each other out, and we're just left with theta v minus theta I. And let's go on to the second part of our trig identity. So we're going to have another factor of 1/2 Vm Im cosine. And now I need to add those two angles together. So omega t plus theta v plus omega t plus theta I is going to look like twice omega t plus theta v plus theta I. So does this expression match with what we observed from the graph that we looked at before? Well, I think it does, right? So if we look at this first part, I think there's something interesting about this in as much as since Vm is a constant, Im is a constant, theta v is a constant, and theta I is a constant, this first part right here represents some constant value or a DC term, right? So we have some DC portion of our power. And as I mentioned a moment ago, this is literally the average power, because this is the average value of our power signal. Exactly half of the time it's above this DC level, and exactly half of the time it's below this DC level. And then we also have this term over here, which is oscillating at exactly twice the angular frequency of either the voltage waveform or the current waveform. So our instantaneous power has two pieces, a DC part that represents the average power, and an AC part that's oscillating at twice the frequency of our voltage or current waveform. So this is our generic representation of instantaneous power. And this equation works for literally anything as long as we are looking at a sinusoidally excited system. Okay. So this is our baseline equation. And let's make some more observations looking at that graph on Desmos again so that we can kind of see some things. Okay. So what do we know about the relationships for the phase angles of a resistor? So phase angle of voltage and phase angle of the current, how are they related to each other in a resistor?
Aren't they just all the same?
Exactly right. So in a resistor, the phase angle of the voltage and the phase angle of the current are the same thing. So I'm going to see what happens if I make both of these have a phase angle of 30 degrees. If I turn off my voltage waveform, now I just see my power. So notice that it no longer dips below the horizontal axis. So everything is constrained to be above the horizontal axis. In this case, it looks like it's centered at 5 and is oscillating between 10 and 0. So we would say that the average power absorbed by a resistor whose voltage is 5 cosine 3x plus 30 degrees and whose current is 2 cosine, 3t plus 30 degrees is 5 watts. All right. This makes sense to me, or our power signal being only above the horizontal axis makes sense to me because we learned on the third day of class that resistors can only absorb power. They can't ever store energy. They just absorb power and convert electrical energy into heat. And that's what this power relationship tells us. Because it never dips below the horizontal axis, it's never supplying any power. Okay, so that makes sense. What about an inductor? What's the relationship between the phase angle of the voltage and the phase angle of the current for an inductor?
The current always lags the voltage, right?
So the current always lags the voltage by exactly 90 degrees. So I'm going to make this phase angle negative 60. Okay. So now there's 90 degrees of phase difference between the voltage and the current, and the current is lagging the voltage by exactly 90 degrees. Well, what does the average value of the power waveform look like now?
Zero?
0, exactly right. So the average power absorbed by an inductor is 0 watts. So effectively, in a steady state sinusoidal system, any pure inductance, exactly half of the time it is absorbing power, and then the other half of the time it is supplying that power back into the system. Okay, we're going to talk about that a little bit on Wednesday when we're talking about complex power, particularly the concept of reactive power and power factor. So just a heads up. So what should we expect, or excuse me, what is the relationship between the phase angle of the voltage and the phase angle of the current in a capacitor?
The voltage always lags the current by 90 degrees.
Yep, so the voltage lags the current by exactly 90 degrees, or another way to put that would be the current leads the voltage by 90 degrees. So I'm going to change this from negative 60, which was lagging by 90 degrees, to positive 120, which is leading. Ooh, that is a minus sign still, plus 120. There we go. So now our current is leading our voltage by 90 degrees. And once again, we can see that the average power absorbed by, in this case, a capacitor is also zero. So exactly half of the time our element is absorbing power, and the other half of the time our element is supplying power. If we go back to something kind of in the middle, so I'm just going to change this phase angle back to zero, we can see that the closer the phase angles are, the less our network winds up supplying power back to whatever our source is, right? So when I have both of these at the exact same phase angle, so effectively a resistor, there is no power supplied by our network. But as I step this down, now there's a little bit, maybe go a little bit faster here. So go back down to zero, go to, negative 30. And this difference in phase angle is just pulling this graph down until it reaches a point where they are exactly 90 degrees out of phase. And then our graph is centered around the horizontal axis. Okay. So we can develop some mathematical relationships to describe all of this stuff as well. Okay. So for a resistor, we know that the phase angle of the voltage and the phase angle of the current are the same thing. And we also know that the magnitude of the voltage is equal to the magnitude of the current times the resistor value. These are relationships that we learned when we were developing our frequency domain relationships. Okay, so I can make a couple of substitutions here, and I can say that for a resistor, so that's why I'm having PR of T. My 1/2 is going to stay. I'm going to substitute in the fact that IM could be expressed as VM divided by R. So I would have VM times VM over R is going to look like VM squared over R. And then what is the cosine of theta V minus theta I going to be? So if theta V and theta I are the same thing, I'm just asking for the cosine of 0. What's that?
1.
1. Okay. I'm pulling my 1/2 VM IM from my AC term now. So I'll have cosine twice omega t. And then when theta V and theta I are equal, the sum of those two angles could be expressed as simply twice theta V. So this expression right here allows us to calculate the instantaneous power absorbed by a resistor if we only know what the voltage drop across the resistor is. So we now have a simpler relationship, but it's only valid for resistors. Our average power is just the DC part of this relationship, which is simply 1/2 VM squared divided by the resistor value. So it looks very similar to our expression for the power absorbed by a resistor in a DC circuit, except that there's this pesky factor of 1/2 that is included, which is because of our trig identity. I can do something similar, and I can express the power absorbed by my resistor only in terms of my current. So that would look like 1/2. Now we're going to use Vm is equal to Im times R. So we're going to have Im times R times Im, or simply Im squared R. Cosine of 0 is still 1. So cosine twice omega t. And now I can say that theta v plus theta I looks like twice theta I. And our average power relationship is then 1/2 Im squared times R. So using these two relationships allows me to solve for my power without having to know both the voltage and the current. I can just know one or the other. Okay. Let's talk about an inductor. So in an inductor, we know that theta v is equal to theta I plus 90 degrees. So the voltage is always leading the current by 90 degrees. And we also know that the magnitude of the voltage is equal to omega L times the magnitude of the current. So the instantaneous power absorbed by an inductor could be written as 1/2 Vm squared over omega L. So what is theta V minus theta I going to be? So let's just write things out right here, right? So theta V is equal to theta I plus 90 degrees, according to this statement. And then we're just going to subtract theta I. Well, the theta i's cancel each other out, and we're just left with 90 degrees. So what's the cosine of 90 degrees?
Is 0.
0, exactly right. So our first term, that DC term, literally goes away, which agrees with what we observed earlier, that our average power in an inductor should be 0. So we're only going to have that twice angular frequency AC part. So that's going to look like cosine of twice omega t plus twice theta v minus 90 degrees. And in terms of only current, this looks like 1/2 Im squared omega L cosine twice omega t plus twice theta I plus 90 degrees. And then our average power is just 0. Lastly, let's talk about a capacitor. So in a capacitor, we know that theta I is equal to theta V plus 90 degrees. And we know that Im is equal to omega C times Vm. So using these two relationships, that allows us to say that the the instantaneous power absorbed by a capacitor is going to be 1/2 Vm squared times omega C. Theta V minus theta I in this case is actually going to look like negative 90 degrees. And the cosine of negative 90 degrees is still 0. So our DC term goes away. And we're just left with an AC term of cosine twice omega t plus twice theta v plus 90 degrees. In terms of our current, this is going to look like 1/2 Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees. And our average power is just the DC part of our instantaneous power, which is once again 0. So just to recap what I've talked about thus far, this expression right here, and I'm about to box it in, is valid for literally any circuit element in a steady state sinusoidally excited system. Okay. So we can technically use this single equation for everything, and we will be correct 100% of the time. The drawback of using this particular equation that I just boxed in orange is that it requires us to know the magnitude of the voltage, the magnitude of the current, the phase angle of the voltage, and the phase angle of the current, which means effectively that both the voltage drop across and the current flowing through our network or element of interest has to be fully defined. For all of these other relationships, which I'll box in light blue down here, we only need to know either the voltage waveform or the current waveform, but not both. But the drawback of them is that they're only usable for these particular circuit elements. So it's not really good for a network, but if we just have a resistor we're interested in, we can use these guys. If we just have an inductor, we can use these. And if we just have a capacitor, we can use this one. All right, so before we move on to the in-class assignment, I want to more formally take a look at the average power. And this is mainly to kind of set up what we're going to be talking about on Wednesday. Okay. So let's say that x of t is a periodic signal. Doesn't necessarily have to be sinusoid. It is just a periodic signal whose period is t. The average value of x of t, x average, is equal to the integral of x of t with respect to time over exactly one period. So I'm going to choose to represent that as from 0 to capital T, but I could just as well have set those limits of integration from negative capital T over 2 to positive capital T over 2, or really any interval that I want, as long as it is over exactly one period of the waveform, right? So I have the integral of my periodic function over one waveform, And then I simply divide by the duration of the period. And that gives me an average value for that periodic waveform. Okay. So in the context of a sinusoidal signal, or our power relationship, so let's look at this, right? So P average is going to be 1 over T times the integral from 0 to T of 1/2 Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I dt. So I'm going to break this into two distinct integrals. So I'm going to have 1 over t times the integral from 0 to capital T of 1/2 Vm Im cosine theta V minus theta I dt plus a second integral from 0 to capital T of 1/2 Vm Im cosine twice omega t plus theta V plus theta I dt. Okay. And let me close that bracket. I want to focus on the right-hand integral first. Purple earlier. So what do you guys think that integral would be equal to? Any thoughts?
Well, we know that everything on the left-hand side is just a constant. And when we're taking the integral of cosine, we're just going to divide everything by 2 again.
So you're 100% right that everything on the left-hand side, and let me underline that, I think I did it in red earlier, is a constant. So we'll unpack that in a moment, but you're 100% correct there. But I'm more concerned about what I have in purple here. So let me bring up Desmos again. Having a program that can describe math is pretty great to me, okay? So I'm going to clear this stuff out, and I'm just going to put in a signal, okay? So 0.5 times 5 times 2, those were my amplitudes earlier, times the cosine of twice omega. So earlier omega was 3, so that's just going to look like 6x, and then plus some generic phase angle. So let's just put in 50 degrees. So whatever theta V plus theta I happens to be. That should be 180. So when we're just looking at the double frequency part, or the part that's oscillating twice as quickly as either the voltage or the current, we just have a simple sinusoid, right? So if I were to integrate this over exactly one period, so that would be from this point right here to this point right here, what would the area under the curve be?
Would it just be 0?
Yes, exactly right. So over exactly one period, the integral of a cosine function or a sine function is exactly 0, because exactly half of the time we are above the horizontal axis, and exactly half of the time we are below the horizontal axis, and our signal is symmetrical. So we could think of it as this area right here plus this area right here. So whatever this is positive and has some value. Whatever this is negative and has the exact same value. We add those two guys together and it just looks like 0. So this whole thing right here doesn't contribute to the average power at all. Okay. So taking the comment earlier that everything on the left-hand side is a constant allows me to pull all of that out of the integration. And so that's going to leave me with 1 over t times 1/2 Vm Im cosine theta v minus theta I times the integral from 0 to capital T of dt. What's the integral from 0 to capital T of dt? Should be capital T, but yeah. So the integral from 0 to capital T of dt should just be capital T minus 0, which is capital T. So effectively, this integral and this 1 over t cancel each other out. So we're multiplying by the period and then effectively dividing by the period. And so what we're left with is exactly what we inferred from earlier, an average power of 1/2 Vm Im cosine theta v minus theta I. So really over the past 40 minutes or so, we've actually looked at the average power in 3 different ways, right? We looked at it as the DC offset of our power signal, because that's exactly what it is. We looked at it as the constant part of our instantaneous power relationship. And now we have fully formally mathematically described it and gotten effectively the same result every different way. So our average power relationship in a steady state sinusoidal system is just going to be 1/2 Vm Im cosine theta v minus theta I. I'm not going to bore you guys with deriving these two formally, because it seems to me that if we got this part with our formal definition, these guys will fall out of that for the same reasoning. All right, so before we move on to our in-class assignment, was there any question regarding instantaneous power and or average power? All right. So let's look at this. So in this first problem, we are told that a linear network has a frequency-dependent equivalent impedance of ZEQ is equal to R over the square root of 1 plus omega squared R squared C squared with an angle of the negative arctangent of omega RC. For what it's worth, that equation is literally the equivalent impedance of a resistor in parallel with a capacitor. So we're told that the resistance is 10 kiloohms and the capacitance is 200 nanofarads. And we are given a current waveform of 2 sine 377t plus 22 degrees milliamps is flowing into the network. And we want to get an equation for the instantaneous power absorbed by this network. So the first thing that I want us to sort out is which equation we should be using for this problem. Anyone have any thoughts?
The second one under the capacitor that we wrote down?
I disagree. So the reason why I disagree is because our network doesn't contain just a capacitor. It contains a resistance and a capacitance. The equations that I gave you guys that I highlighted or boxed in this light blue color are for if we have just a capacitor, just an inductor, or just a resistor. Okay. But because our network has some resistance and some capacitance, none of those can be applied. So that means the only one that will work for this particular situation is the first relationship that works for literally anything. Okay. So does that line of reasoning for why I'm choosing the first equation make sense?
Yes.
Okay, I just want to make sure it's clear because it can be tricky. I just hit you guys with effectively 7 different relationships. They're all related to each other. And I want to make sure that you understand where you can apply each one. Okay. So the relationship that we're ultimately going to wind up using is that our instantaneous power is equal to 1/2 times the magnitude of the voltage times the magnitude of the current cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. And so now it's our job to figure out all of those constituent little parts, right? So in order to apply this equation, we're going to need to know the magnitude of the voltage drop across our network, the magnitude of the current flowing through our network, the phase angle of the voltage, the phase angle of the current, and omega. So we have 5 different pieces of information that we need to figure out in order to apply this equation. So let's start with things that are given to us. Okay, so which of these pieces of information were legitimately just given to us? What's omega?
754.
I disagree. It's right here.
Oh, I was looking at the answer. My bad.
Yep. So you told me what twice omega is, but omega is always just the thing that's multiplied by our variable t in our sinusoid, right? So omega is 377 radians per second based on the problem statement. So I'm just going to underline that in the exact same color that I underlined it over here. So there's omega. Okay. What's IM? The magnitude of our current waveform.
Two.
2 milliamps. So, okay. And that was given to us right here. What's theta I?
$22.
So that's a trick question because this is a sine function, right? Whenever we're dealing with any of our steady state sinusoidal analysis, we need to convert everything into cosine functions. So I intentionally put this one as a sine function to trip you guys up. So that's something that you should always be looking for. How do we convert from sine to cosine?
Subtract 90.
Subtract 90. So 22 minus 90 is, if I'm not mistaken, negative 68 degrees. Let me double check that on my calculator. 22 minus 90. Yep, negative 68. So those are the, well, two pieces of information were directly given to us. Theta I, we had to do a little bit of work for. So the only things that were left to figure out is the magnitude of the voltage and the magnitude, excuse me, and the phase angle of the voltage. Anyone have any thoughts on how we might figure those out?
Well, we can probably convert to polar form for ZEQ, and then we can also do that for the current equation and then divide.
It'll be multiply because of Ohm's law, but you're on the right track, right? So Ohm's law tells us that the phasor voltage V is equal to the phasor current I times the impedance. So effectively, V is just going to be I times ZEQ. 100% correct there. All right, so let's figure out what's going on with ZEQ. So it's got some magnitude that we can literally just plug stuff into our calculator, and then it's going to have some phase angle that we can literally just plug stuff into our calculator with. So I would like for you guys to take a moment and plug in R is equal to 10 kiloohms and C is equal to 200 nanofarads and tell me what the magnitude of my impedance is going to be. Nano is times 10 to the minus ninth, by the way.
Will it be 16,610? Or I mean, I
That
don't know
is
what the
incorrect. Anyone else get a number? All right, well, I got 7,984.643 and some change ohms. And I know that number to be correct because I recognize it from the past several years that I've been using this problem. Just as a heads up, one very common mistake that people seem to make is forgetting that they need to square things. Your calculator can sometimes run out of memory. I know that mine did, so I had to break this calculation up into two different parts. But the correct answer for that part is 7,984.6. Our phase angle should be a little bit easier. So that's the negative arctangent of 377 times 10 times 10 to the 3 times 200 times 10 to the minus 9. And I get an angle of negative 37.016 degrees. So using that value for ZEQ, our voltage is nothing more than 0.002, so that's 2 milliamps, with an angle of negative 68 degrees, times that 7,984.643, with an angle of negative 37.016 degrees ohms. And I got 15.969 with an angle of negative 105.016 degrees volts. And this part right here is VM. And this part right here, including the negative sign, is theta V. So VM is 15.969 volts. And theta V is negative 105.016 degrees. So plugging in all of these values, our instantaneous power is then 1/2 15.969 volts times 2 milliamps cosine of negative 105.016 degrees minus negative 68 degrees plus 1/2 15.969 volts times 2 milliamps times the cosine of twice 377t plus negative 105.016 degrees plus negative 68 degrees. And so now I'm just putting stuff in my calculator. So 0.5 times 15.969 times 2 times 10 to the minus 3. So that's going to look like a 0.01596. So let's call that 0.1. Oh, actually. 15.969. That's going to wind up being in milli. cosine 754t minus 105.016 minus 68 negative 173.016 degrees. And then for the part out front, I just take that and multiply by cosine of negative 105.016 plus 68. And that seems legit. Okay, so one thing that I want to make very clear here is that effectively, as far as circuit analysis is concerned, we finished up learning that part of things last Friday. This section and most of the subsequent sections are all just effectively equations, and we just need to make sure that we know which stuff to plug in and where. And so that's why I worked this problem out in that particular way, okay? I identified the equation that I would ultimately have to use in order to give me the instantaneous power. And then I just figured out how to get those individual parts, right? So omega was from the problem statement, IM was from the problem statement, theta I was effectively from the problem statement. The VM and the theta V are just the parts of the phasor voltage. So even though our answer is explicitly a time domain relationship, we are using our frequency domain equations or relationships to get those parts, okay? So all of our circuit analysis is going to happen in the frequency domain, and then we just plug those values into our time domain equation. Any questions on this particular problem? All right. So if we look at our second problem, we're told that we have three circuit elements that are connected in parallel. A current source, I'm going to assume the direction is up. A 1 kilo ohm resistor, and a 15 millihenry inductance. And we are asked to calculate the instantaneous power absorbed by each of these elements at a particular time. So going back to what I said a moment ago, all of our circuit analysis that we need to apply in order to determine the things that go into our equations is going to happen in the frequency domain. So I want to convert this circuit into the frequency domain first, okay? So what should my phasor source current be?
The 100 angle 0.
100 angle 0 milliamps. So I'm going to simplify that and call it 0.1 angle 0 degrees amps, just so that I'm in base units. Okay. So 0.1 angle 0 degrees amps. What is our 1 kilo ohm resistor going to look like as an impedance?
Still 1 kilo ohm.
Still 1 kilo ohm. Thank you for that, Baylor. And then lastly, we have our inductor over here. So what is my 15 millihenry inductor going to look like as an impedance?
J omega L.
So J omega L, what's omega?
The 2 times 10 to the 5th.
Okay, so 2 times 10 to the 5 times 15 times 10 to the minus 3. So let's see. So that's 2 times 15 is 30 times 10 to the positive 2 is 3,000. So J3 kiloohms. Throw it in your calculator if you want to make sure, but I'm 99% sure that's right. Okay, so we have converted our circuit from the time domain into the frequency domain. And our ultimate goal is to calculate the instantaneous power absorbed by each element, okay, at a particular time. So let's start with our current source, okay? So for our current source, because it's a source, so it's not a resistor, capacitor, or inductor, we have to use our generic equation. So that's the 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine, twice omega t plus theta v plus theta I relationship. Now, I believe that we know what we know what Im is, and we know what theta I is, because it's just the current supplied by the source, right? So how might we go about finding our phasor voltage? Let me be explicit here and say that this is the phasor voltage that I'm looking for.
It's just going to be our current source, and then we can do current division, and then multiply whatever answer we get there by 1 kiloohms.
So we could. You're adding an unnecessary step. Okay, so there's nothing wrong with what you said that would absolutely work, but I would argue that if we just multiplied our current by 1 kiloohm in parallel with J3 kiloohms, we'd get the same result in a single step instead of breaking it into 2. Does that make sense?
Yep.
Okay. So that's how I'm going to choose to do it. So V would be equal to 0.1 angle 0 degrees amps times, so 1 kiloohm times J3 kiloohms over 1 kiloohm plus J3 kiloohms. So 0.1 angle 0 1,000 times 3,000 I over 1,000 plus 3,000 I is 94.868 and some change, with an angle of 18.435 degrees. Now, just plugging things in, and actually PCS of 10 microseconds, so that's 10 times 10 to the negative 6 seconds, is going to look like 1/2 times 15 point, that's from the last problem, brain fart, 94.868 volts times 0.1 amps times the cosine of 18.435 degrees. What should our phase angle for our current be?
Zero.
So here's where I kind of disagree. And I know this is going to sound weird, but we were asked explicitly to calculate the instantaneous power absorbed by each element. Well, this current is flowing into the negative polarity terminal, so 0 degrees is the current is for supplied power. So what we could do here is put 0 degrees in, and then whatever answer we get, we would simply have to multiply it by a factor of -1 to get our absorbed power, or we could set the phase angle to be 180 degrees out of phase, which is just changing the direction of our current, and we would get the correct answer from the jump. So that's why I'm choosing to put my phase angle as positive 180 degrees here. That makes my current flow into the positive polarity terminal. Continuing our calculation down here, we're going to have 1/2 94.868 volts times 0.1 amps times the cosine of twice 2 times 10 to the 5. Let me put something here to be very explicit. Radians per second times our time of 10 times 10 to the -6 seconds. And now I'm going to add 18.435 degrees plus 180 degrees. And again, if you don't like adding the 180 degrees to the current phase angle, you could get away with just multiplying by a factor of -1 at the end, based on our understanding of the passive sign convention. I left a blank here between things because I want to point something out. So this bit right here that I've underlined is going to give us an angle in radians. And this bit over here is going to give us an angle in degrees. So we need to convert either the bit that I've underlined in red from radians into degrees, or we need to convert the bit I've underlined in purple from degrees into radians. Now my calculator is almost always left in degree mode, so I'm going to choose to convert that first part into degrees. And I'm going to do that simply by multiplying by the conversion factor that I've been using in Desmos, except the other way around, 180 degrees over pi. So that makes sure that the angle for the first part is in degrees and the angle for the second part is in degrees, so that my calculator doesn't have a panic attack. So plugging all this stuff in, so 0.5 times 94.868 times 0.1 times the cosine of 18.435 plus 180 gives me negative 4.49999. So let's just call it 4.500. So that's my DC part from the first bit. Now I'm going to do the second part. So 0.5 times 94.868 times 0.1. And that gives me 4.743 And now I'm going to do that cosine bit. I'm just breaking this up into smaller parts so that my calculator doesn't freak out too hard. So cosine of 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 18.435 plus 180, 0.3807. Let's just call that 381. Putting all those things together. So negative 4.5 plus 4.743 times my previous answer. I get negative 2.6939, so negative 2.694 watts, which is exactly what we were expecting. So to me, the hard part of this stuff is actually just making sure I put everything in my calculator right, because the equation is so large that it's easy to make a mistake. Once again, the circuit analysis portion of this is literally nothing that we haven't done before. So any questions on how I calculated the instantaneous power absorbed by our current source? All right.
So why did you add 180 instead of going to 0?
So 0 degrees is the current that's flowing from the negative polarity terminal, so into the negative polarity terminal, out the positive polarity terminal. Because we were asked to get absorbed power, I need the current flowing in the opposite direction. So negative 0.1 angle 0 degrees amps is the same thing as positive 0.1 angle plus or minus 180 degrees. Amps.
Okay, and did you just change it to degrees because we had a time like the previous problem we didn't do that?
Exactly right. So for the previous problem, let me scroll up here. We were looking for a function, right? So we have 754 radians per second times time, nothing big there. But in this particular problem, you're exactly right. Because we were given a time to evaluate this at, we ran the risk in our calculations of having an angle that was in radians on this side and an angle that was in degrees on the right-hand side. And we just need to make sure that all of our angles are of the same unit. I chose to convert my angle in radians into degrees because my calculator is in degree mode and I'm lazy. Any other question on our current source power calculation? All right, so let's move on to our resistor. Okay, so because we're dealing with a pure resistance, we should be able to use one of our resistor equations. Which one do you think we should use?
Definitely the one with the current, since we already know that. Although we do also know voltage.
So I would argue that we do know the voltage across the resistor, and we do not currently know the current flowing through the resistor. We could get the current by using current division, but that's overkill since we already know the voltage, right? Because all of these elements are connected in parallel, the voltage is common to all of them. So I think we can get away with just using the relationship PR is equal to 1/2 VM squared over R. Let me write that better. Got away from me. Times 1 plus cosine twice omega t plus twice theta V. Because we know the voltage drop across the resistor and the resistor value, so we have all of the information we need. So this seems like a good one to use. So that's going to be 1/2 times that 94.868 volts quantity squared divided by 1 kiloohm times a factor of 1 plus cosine of 4. Actually, let me write it the same way I did a moment ago. Twice 2 times 10 to the 5 radians per second. 10 times 10 to the minus 6 seconds. 180 degrees over pi plus 2 times 18.435 degrees. So putting this into my calculator, 1/2 94.868 squared over 1,000. So that looks like 4.5 times 1 plus, and now I'm going to do all the cosine bit. So 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 2 times 18.435 negative 0.0688 and some change. All right, so let's see. 1 plus answer times 4.5 gives me 4.190 watts. And there we go. Any questions on our calculation for the power absorbed by the resistor? All right, so you guys tell me what my equation that I should use for the inductor is.
It's going to be 1/2
1/2
Vm squared over
Vm
omega L.
squared over omega L. Sorry, I was writing C there. Thank you for that.
And then cosine 2 omega t plus 2 theta v minus 90 degrees.
There we go. Absolutely right. That's the one that I would use as well. And once again, we have all of the information that we need to apply this equation. So it's just plug and chug. So that is going to be 1/2 times 94.868 volts squared. What's omega L? It's literally the impedance of our inductor without the J. So I'm just going to put in 3 kiloohms down there. Multiply that by cosine of, these braces like I did, twice 2 times 10 to the 5 radians per second, 10 times 10 to the minus 6 seconds, 180 degrees over pi, plus twice 18.435 degrees minus 90 degrees. And just tossing this in my calculator. So I get 1.5 for that first bit. Now I'm doing all of the cosine stuff. So cosine 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 2 times 18.435 minus 90, which looked like negative 0.998. And I get negative 1.496 watts, which got a little bit of rounding error, but that's close enough for me. Any questions regarding this particular calculation? All right. So lastly, we have a problem here where we're just asked to determine the average power absorbed by each element in our network. Okay. So we want the average power absorbed by the sources, the average power absorbed by the resistor, and the average power absorbed by that capacitor. So let's start with something simple. What's the average power absorbed by literally any capacitor?
0.
0. Boom. Don't need to do any work for that whatsoever. For our current source, we need to know the voltage drop across the current source. So I'm just going to call that this voltage VR. So the voltage drop across the current source is the exact same thing as the voltage drop across that 4 ohm resistor. Notice that the current would be flowing into the negative polarity terminal and out the positive polarity terminal. So we would wind up doing a 180-degree thing here for that particular calculation. Or like I said earlier, we can literally just throw a negative sign out front and it'll give us the same thing. So I'll probably choose to do that route this time. To get the power absorbed by my voltage source, I'm going to need to know the current that's flowing through my voltage source. I'm going to call this current IC because it's also the current that happens to be flowing through our capacitor. So how do you guys think we should approach this problem to determine either of those two phasor quantities?
Well, we could turn off one of the sources.
So you're suggesting using superposition. Seems
Yes.
seems okay to me. So using superposition, so let's start with current source on and voltage source off. We're going to have 12 angle 0 degrees amps, 4 ohms minus J2 ohms. That is a short circuit. This is VR prime. This is IC prime. So how could we solve for either of those quantities?
We can just do current division to find IC here.
Okay, perfectly reasonable. So IC prime would be 12 angle 0 degrees amps times 1 over negative J2 ohms divided by 1 over 4 ohms plus 1 over negative J2 ohms. If you have any questions about that current division relationship, don't hesitate to ask. So I got 10.733 with an angle of positive 26.565, excuse me, amps, and I'm storing this in my calculator as X. Knowing that current, how could we get VR prime?
We could just multiply by negative J2 ohms.
Exactly right. So because the capacitor and the resistor appear in parallel, since we have that capacitor current, multiplying it by the impedance of the capacitor gives us the voltage drop across both the capacitor and that resistor. Perfect. So IC prime times negative J2 ohms, which I get to be 21.466 with an angle of negative 63.435 degrees volts, and I'm storing that as Y. Okay. Anybody have any questions or concerns about our circuit analysis for current source on, voltage source off? So from here then, let's go to current source off and voltage source on. So with our current source off, it's just going to look like an open circuit. Here is our 4 ohm resistor minus J2 ohm capacitance. I need to scroll up and look at what this is. 4 angle 30. Here is VR double prime. Here is IC double prime. So how could we solve for either of those quantities?
We just do a voltage division for the 4 ohm resistor
All
to
right.
get the 4R or the VR no prime.
Sounds easy enough to me. So VR double prime is going to be 4 angle 30 degrees volts times 4 ohms over 4 minus J2 ohms. I got that to be 3.5777. So let's call that 3.578 with an angle of 56.565 degrees volts. I'm going to store this as T. What about that current IC double prime?
Could you just do the VR double prime divided by 4 ohms?
I need to make one modification. So VR double prime divided by 4 ohms is going to give me the current flowing down, which is the current in the opposite direction of the one that we're looking for. So I will need to add a negative sign out front. So negative VR double prime over 4 ohms. And that looks like 0.894 with an angle of negative 123.435 degrees amps, and I'm storing that as Z. So let me just double check something here real quick. All right, so from here, I can say that IC is just IC prime plus IC double prime, which should be X plus Z, or 9.9685. So let's call it 9.969 with an angle of 23.994. Amps, and I'm going to store this as A. And then VR is VR single prime plus VR double prime. So that is Y plus T. .9198, so 920, angle negative 54.43, excuse me, 4866. So let's call that 487 degrees volts, which I'm storing as B. Okay, so let's do the current source first. Okay. So our relationship should just be 1/2 Vm Im cosine theta V minus theta I. Because our current is flowing into the negative polarity terminal of our voltage source, that's giving me, excuse me, this current times this voltage is giving me supplied power. So I'm just going to choose to put a negative sign out front to take care of that. Okay. So that's going to look like negative 1/2 times 19.920 volts times 12 amps cosine negative 54.487 degrees minus 0 degrees. I got negative 69.428 watts. Let's just check. Seems okay. For our resistor, what relationship should I use? So do we know the voltage drop across the resistor, or do we know the current flowing through the resistor?
We know the voltage drop.
Yep. So my relationship should just be 1/2 VM squared over R. So that's 1/2 19.920 volts squared divided by 4 ohms. So 19.920 squared divided by 2 times 4 is 8. 49.601. Just double check that. And there we go. For my voltage source, we're going to have to use the same relationship that we used for our current source. But I just want to be clear here. So we defined our current IC as flowing into the positive polarity terminal. Since we're asked for absorbed power, we're just going to use that relationship, but we don't need the negative sign this time because our situation isn't set up for supplied power. So using this equation from above, we're going to have positive 1/2. The magnitude of the voltage drop is 4 volts. The magnitude of the current was 9.969 amps. Cosine, the phase angle of the voltage was 30 degrees. The phase angle of the current was 23.994 degrees. So plugging this in, 0.5 times 4 times 9.969, cosine 30 minus 23.994. I get 19.8285, so 829 watts. And again, a little bit of rounding error there, but no big deal. All right, any questions regarding the circuit analysis that we did or any of the calculations that we did to solve this?
Why is PC 0?
Oh, the average power absorbed by a capacitor is literally always 0. So let's go back to our relationship.
Oh, that was the, yeah, that was an equation. My bad.
Yep. No, not a problem at all. This is new to you guys, so ask as many questions as you need to. Anything else?
Dr. Hartman, I have one question.
Yes.
When you were graphing the sinusoids on Desmos, the waveform above the x-axis was what represented the power supplied, correct?
No. So if we look at this, so let me, if this value of px that we got here was determined by a current that was flowing into the positive polarity terminal, then everything above the horizontal axis represents an absorbed power, and everything below the horizontal axis represents a supplied power.
Okay, that makes a lot more sense. Thank you.
Yeah, no problem.
I had a question about the test.
Sure.
When is the earliest we can take it next week?
I don't remember what the syllabus says. Let me find it.
If it's on there, I can look at it.
No, it's not what
It says review day is Monday and then the test is Wednesday.
So if the review day is Monday, then I will have it set to where you could take your test Monday afternoon. So like Monday, or I guess Monday night, and then Tuesday afternoon, Tuesday night, Wednesday afternoon, Wednesday night.
Thank you.
No problem. Any other questions? All right. Well, I hope you guys have a great rest of your afternoon. On Wednesday's class, we are going to discuss effective values for periodic waveforms, and that will lead us into complex power. So see you guys on Wednesday.